Hello and welcome back to Fourier Transform. This is the video series where we talk a lot about the special integral transform. And indeed, in today's part 31, we will finally see how the inverse transformation looks like. This is the so-called Fourier Inversion Theorem, and we will formulate it for the rapidly decreasing functions. In fact, we will show that the Fourier transform restricted to the special function space is a bijection. However, as always, before we start with that, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And moreover, as a Patreon or Steady member, you are able to download the additional material with the link in the description. I always recommend having the PDF versions of the old videos ready when you watch a new video here. And with that said, let's immediately start with the Fourier transform written as a curved f. And as already mentioned, we will restrict it to the Schwarz space, which consists of rapidly decreasing functions. And now the first thing we will show is that the output space is actually also given by the Schwarz space. Moreover, we will see that this map F is an isomorphism on this space. This implies that the inverse map of F exists and it can be written as a nice formula. This is a really helpful result because it tells us that we can go back and forth with the Fourier transform. And indeed, in the last video, we have already seen one important example where the inverse of the Fourier transform is quite clear. So please recall that this Gaussian function here does not change under the Fourier transform. Hence, applying f gives you exactly the same function back, but you would use the variable name p instead of x. So in this example, the inverse is also quite clear because nothing changes. And at this point, I can already tell you that we will use this function later on, so let's give it a name. So let's simply call it capital phi of x. However, scaling the function will be really useful because we want that the integral is equal to 1. And from the last video, you already know that the integral of the Gaussian function is the square root of 2 pi to the power n. And since the Fourier transform is a linear map, it does not care about such a factor in front of the function. Therefore, the Fourier transform of phi is phi again. And now let's formulate the first proposition of the video. Namely, we want to have, regardless which function f from the Schwarz space we put in, a function from the Schwarz space comes out again. In fact, this is needed if we want to define the inverse on the whole space again. And this one is actually quite easy to see because we already have all the ingredients we need for the proof. We just need the formula from part 29 that connects differentiation with multiplication. More precisely, a partial derivative del j can be pushed into the Fourier transform and becomes a multiplication operator. And there it's quite obvious that multiplying a Schwarz function with a polynomial gives us a Schwarz function again. This means that we can easily apply a partial derivative to the result and apply the formula again. In other words, no matter how high the order of the partial derivative is, it always exists. So the short way to write this is that d alpha of f hat exists for all multi-indices alpha. Therefore, we immediately get that the Fourier transform of f is a C infinity function. So the only thing that remains to show is that we are still rapidly decreasing. And please recall this important property that can be described by such a supremum. This means when we multiply any derivative by a polynomial, then this should still be a bounded function, regardless which orders are involved here. So we have this property for f, and now we also want to have it for f hat. And there you might already recognize that on the left we have a multiplication operator and on the right we have a differentiation operator. And now the trick we can apply is simply that the Fourier transform exchanges the roles of these two operators. So maybe to keep it short, let's call the one operator just d and the other one m. So in short, what we have here is m applied to d applied to the Fourier transform of f. And then in the next step, we just push them into the Fourier transform. And then we can use part 29 as many times as we need it, and roughly we know that the differentiation operator becomes a multiplication operator, and the multiplication operator becomes some sort of a differentiation operator. So I don't want to write down the details because there are always some factors I involved, the important thing for us is that we have some new operators. And applying them to a Schwarz function f gives us a Schwarz function again. So we know that the Fourier transform here is well defined and that we get a continuous function out. In fact, this was one of the first results we had for the Fourier transform, and moreover, we also know it's a bounded function. And this is the crucial part, because it tells us that this supremum here is finite. And maybe to keep it consistent, we should also use the variable name p here. And now you see, this argument works no matter which polynomial we choose and which multi-index alpha. And for that reason, f hat is also a Schwarz function. So please remember for the future, the crucial part here is how the differentiation and the multiplication operators act under the Fourier transform. And please note, this result allows us to apply the Fourier transform as often as we want, and this will lead us to the inversion formula. So this inversion theorem will tell us how we can come back to f if we only have the Fourier transform of f given. So let's take a rapidly decreasing function f and its Fourier transform f hat. And now we can also integrate f hat together with a complex exponential function. However, in contrast to the Fourier transform, let's use a plus sign in it. Otherwise, everything else should be similar, which means we also integrate over the whole space and we have the same factor in front. And you know, this one is 1 over the square root of 2 pi to the power n. And this is already the whole inversion formula, because what we get back is our f of x. And please compare this formula to the similar formula we have for the Fourier series, and then you are allowed to say that having the frequencies allows us to reconstruct our original function f. However, please always remember that for the continuous Fourier transform, everything is formulated by using integrals. In fact, this property makes it possible to see the integral on the right hand side as an ordinary Fourier transform again. As you can see, it's just the Fourier transform of f hat again. The only difference is the sign in the exponential function, which means we evaluate this Fourier transform at the point minus x. In other words, applying the Fourier transform twice in a row is just a reflection in the x-coordinate in the end. So the Fourier transform f might be a really complicated operator, but f squared is a really simple one. And now I can tell you, we have all the stuff we need to write down a formal proof of this formula. And maybe not so surprising, the Gaussian function capital phi goes in. And as you might already know, the graph of the function can be sketched like that. The graph is symmetric with respect to the y-axis, so the function does not care about this sign here for x. However, this is not so important because we already know that phi does not care about the Fourier transform anyway. But the really important thing is now that I want to make this function thinner and thinner, such that it is more and more concentrated around the origin. So more precisely, we will scale the function in the domain and the codomain such that the integral still stays the same. So maybe you have already seen a construction like that. The result we get is what we call a Dirac sequence. And therefore the common symbol one uses here is a delta with index k. Hence for every natural number k, we have a function delta k, which is just phi, where we scale it in the domain, which means we have k times x, and we also scale the value, which means that we have k to the power n in front. And by using this definition, we immediately get the three properties that define a so-called Dirac sequence. The first one is quite simple, the function is just non-negative, and this one is clearly given. And the second one, as already mentioned, just tells us that the integral stays the same in the whole sequence. And there you see, this is the reason why we chose this factor in front of the exponential function, because it tells us that we get the integral as 1. Indeed, this statement is quite easy to show, because you just need one substitution in the integral to go back to phi. But now comes the most important property of a Dirac sequence, namely, it's concentrated around the origin. More precisely, this concentration should get better and better when we increase our index k. And now we can describe this behavior by just choosing a small epsilon ball around the origin. And then the integral of delta k, where the ball is excluded, should get smaller and smaller. Or more concretely, in the limit this should go to 0 no matter how small the epsilon ball was chosen. So this is a general property of a Dirac sequence, and we can also show that this one is satisfied for our definition above. So you might already know that with such a Dirac sequence we can do a lot. For example, there is a famous approximation theorem that is applicable to bounded continuous functions. In short, it tells us if we use the convolution delta k with f, then we have a uniform convergence on compact sets. So we get a nice approximation for continuous functions. If you want to know more about this approximation theorem, you can check out the video I have about it. In fact, we don't need the full power of it, because we know that the pointwise convergence is included in the uniform convergence. And this is the only thing we need here. On the other hand, we also need the behavior of the Gaussian function under the Fourier transform. And obviously at this point now you know this means that the Gaussian function does not change under the Fourier transform. So whenever we have phi involved, we can also take phi hat. And moreover, we also have the symmetry of the Gaussian function, so instead of plus we can also put a minus sign inside without changing the value. So this is what I want to do here, and then we can see delta k as an integral as well. And since it's the Fourier transform, we have the same factor as always included. And instead of the variable p, we now have minus k times y. And otherwise it's just the same integral as always. And now the next thing I want to do is to substitute x by z over k. I do that to bring the exponential function here into the form we want to have. So you see the whole thing here just allows us to rewrite our delta k. And moreover, this substitution also cancels the factor k to the power n. And at this point you should see that the exponential function is e to the power plus I, as we want to have it in our inversion formula. So indeed we are almost there, we just have to put everything together now. So you could say what comes now is just some calculations with integrals. But please don't forget what we want in the end. We want to have an integral formula for f of x. And the first thing we can apply here is the pointwise convergence for the convolutions with delta k. So we have to evaluate the convolutions at the point x and then form the limit k to infinity. And by using the definition of the convolution, we have a limit of integrals. More precisely, it's delta k of y times f of x minus y. So this is just the definition of the convolution, but now you see, instead of delta ky, we can use this whole integral here. So let's use that to get iterated integrals. And now you might realize what we want to do here is to use Fourier's theorem to exchange the order of the integrals. Indeed, this is not a problem at all, because everything here is integrable anyway. Therefore, let's put the integration with respect to y in the middle. And there you see we have the nice exponential function together with our Schwarz function f. So by substituting x minus y, we can bring this to our ordinary Fourier transform. And you see this substitution is quite simple, we just get a second exponential function in. So maybe let's do it together here. Instead of x minus u, we just have u, and dy is the same as du. But now in the exponential function, instead of y, we have x minus u. So we have x in the inner product with z with a plus sign, and u in the inner product with z with a minus sign. And obviously we need the one with the minus sign, and the other exponential function we can just pull out. So let's put this in front of the integral. And moreover, we can also push this factor here to the correct integral, and then we have our Fourier transform as always. So you see, the integral here with respect to u is actually just f hat at the position z. So this makes the whole formula already much shorter, and then in the next step I want to push this limit into the integral as well. And as always, this step is justified by Lebesgue's dominated convergence theorem. In fact, in order to apply it, we have to check for an integrable majorand, but f hat is integrable and phi is definitely bounded. So the whole thing is not a problem at all, and what we get out here for the limit is just phi at 0. And by putting the origin into the Gaussian function, we see that we get exactly the factor as always. So we have 1 over the square root of 2 pi to the power n, and the whole inversion formula is there. So maybe the only thing you would change here is the name of the variable. So by using the variable p, this looks like the inverse Fourier transform as we want to have it. So indeed, the Fourier Inversion Theorem is proven. We needed to do a lot of calculations to get this nice formula, and therefore in the next step, let's embed it in the theory again. But obviously this should be something for the next video, so I really hope I meet you there again, and have a nice day. Bye bye.